Okay, so as we're going to push towards deriving a model for the Euler or elastic buckling load, we're going to do something that we've really not ever done before. And that's to draw the free body diagram of a system in its deformed position and take account of that deformation. What we mean here is that we've got this buckled member, right, that has this sort of arc that comes along here. We don't know what exactly the geometry of that arc looks like just yet, but we're going to come in at its maximum location. If that's a symmetric arc, of course, that would be in the middle. So I'm going to put a little reference line in here. That's the vertical or undeformed or undisplaced, if you prefer that term, position. And then we'll put in the little arc. The aspect of having it as where at its maximum is that the slope of that curve will be 0, and that'll be kind of important to us here in just a second. Right, so there's our displaced position or deformed position, and then we've got our axial load. Right, when it happens, that's at P critical. So we have then an axial load in the displaced position that is offset. Of course, by axial equilibrium, that's going to, these two will be equal in opposite, right? This is purely vertical because the centroidal axis, the longitudinal axis that is of the member right at this point, is going to have 0 slope, right? Now, it is offset though, and that's a critical thing then to realize, right? And we're using that little symbol lowercase v here. Some text and people that derive this will use lowercase y for that deflected position, right? Now the member is bent, right? Now this will seem a little weird here. The way the bending is, clearly the compression side is on the left, and so the actual physical moment is acting to the left. But when you regard that our sign convention is such that up is now positive, what you've got shown here is frowny face or negative bending moment. That's a little weird, right? But here's the key, I think, in trying to understand and work through the derivation. Show all the internal forces in their positive sign convention when it comes to moment and shear, which in this case would be like this. We can anticipate that the actual moment has to go in the other direction, and that will be revealed eventually. All right, so now we're just going to use all those good things that we learned in statics. Right, so we'll come along and we'll sum moments about this point right here. Point 0 would be, we could do it at the top if we wanted to either, but note, the key is that the two axial forces are parallel to each other. They're a force couple. So when we look at equilibrium, then we've got sum of moments about point 0. Let's take then counterclockwise as positive. We'll have then our moment, so our internal moment, plus P critical times our little eccentricity that we've got here, which is V. And that has to all equal 0. Now remember, I said that this would eventually reveal that the moment has to be going in the opposite direction. Sure enough, right? You take the moment to the other side, there's a minus sign, it has to be going in the opposite direction. But hold on, we don't want to really quite look at it that way. We want to instead connect back up to our critical expression of moment curvature, that M is equal to EI kappa. Kappa, of course, is 1 over the radius of curvature, but it is approximated by the second derivative of our displaced shape. That's going to be our key, right? And so what we'll have is then when we substitute in for the moment, EI V double prime, second derivative of V, that's the curvature, plus P critical times V is equal to 0. Right now, whenever you see non-zero, well, not non-zero, but whenever the constant in front of the V double prime is not 1, think about dividing through by that constant. And that's what we'll do. P critical over EI times V is equal to 0. And that equation is of the form of second derivative plus a constant squared times v is equal to 0. You're like, I don't see any squaring going on. Why did you do that? You'll see why in the solution of this equation shortly. But c squared is equal to p critical over EI. Remember, what we're after is to figure out what that critical load is. And we already are starting to see how it, some of the key things that are going to come along. If we can only find out what the constant is in this equation in relation to the solution, then we'll be in really great shape. Before we go on, though, there's some family housekeeping to take a look at, and that is the name of this equation, right? This is a differential equation, right? We've got differentials in here. It has constant coefficients, right? The constant's not our function of x or anything like that. So this is with constant coefficients, right? But there's a lot more to this, right? This is an ordinary differential equation. What would be not ordinary? A partial differential equation, right? So our little v here is just a function only of x, right? So it's an ordinary differential equation. It is all set equal to 0, so it's a homogeneous ordinary differential equation. The function, little v, has all to the first power, right? We don't have any squaring operation on the v itself, so that makes it a linear homogeneous ordinary differential equation with constant coefficients. And because the highest order derivative that we have there is the second, then that makes it a second order linear homogeneous ordinary differential equation with constant coefficients. Now this turns out to be a model that shows up over and over throughout engineering and science. It relates to how things vibrate, and particularly how musical instruments make music. And as such, this is also called the harmonic equation. Right, so we'll go find the solution of that shortly.